We will now start talking about iterative solvers. We spent the first part of this series of lectures talking about direct solvers, and we specialized with the Thomas algorithm, which dealt with tridiagonal matrices. Today, we're going to start talking about iterative solvers, which is the second category, second class of solvers for linear systems of equations. Before we get started with iterative solvers, we need to talk a little bit about sparse linear systems. You will notice as you go through your career that the vast majority of chemical engineering applications, even mechanical engineering, civil, anything that involves fluid flow, transport, gas dynamics, things with heat transfer, things numerical, partial differential equations, you will encounter a very special class of linear systems known as sparse matrices, sparse systems. An example of this is the heat transfer problem, the steady state heat equation that we just did in class, where you are converting a continuous differential equation into a set of algebraic equations, and we get these sparse systems. The reason being is that as we turn the equation into discrete points, the points are only connected, each point is only connected to a few neighboring points, which creates this very large system of what we call sparse equations. So what are exactly sparse linear systems? They are systems where the matrix representation is essentially all zeros. It's mostly zeros. And specifically, the mathematical definition of a sparse matrix is given by a number called the sparsity. And if a matrix has a sparsity greater than 0.5, then we call the matrix sparse. And what is the sparsity? It's nothing more than the ratio of the number of zero-valued elements in the matrix over the total number of elements. So if you had a matrix that is 10 by 10 and it has 100 elements in it, if 51 of those elements are zeros, then the matrix is sparse. Even if 50 of those elements are zero, we call the matrix sparse. In other words, if more than 50% of the entries in a matrix are zero, then the matrix is sparse. Again, these sparse systems arise from ODEs, PDEs. We just mentioned a couple of examples. But the key thing is that attacking these systems with direct methods is very, very inefficient for many reasons. We will talk about storage of sparse matrices a little bit later, but we have a special class of methods designed for sparse matrices, and we call those iterative methods. And now we can begin our discussion about iterative solvers. And the idea of iterative solvers is, hey, let's start with a guess for the solution and then come up with a recipe, a formula to improve this guess, okay, so that we can get close enough to the true solution. And earlier on in class, I had discussed the rationale behind iterative solvers, saying, hey, we don't need to get the solution exactly since the system is anyway an approximation. The initial equations are already an approximation to a system. Why worry about solving those exactly? Hence the idea of iterative solvers. There are numerous approaches. I mean, the topic of iterative solvers is a very well-researched field, and there are people who have dedicated their lives to understand iterative solvers and design iterative methods. In this class, we will only touch upon the simplest of iterative methods, but they will teach you an important lesson that there are methods out there that can solve linear systems of equations very efficiently. You will hear methods. So we will talk about the Jacobi method in this class, which is the simplest one, to complex Newton-Krylov and multi-grid methods. When do we use iterative solvers? When it is faster to solve iteratively than directly. So typically for large sparse systems of equations. Again, we're not talking about a 10 by 10 or 100 by 100 system. We're talking about million by a million and trillions of entries in a matrix. Now, sparse systems of equations that are diagonally dominant. So one requirement for iterative solvers is for the matrix to be diagonally dominant. What that means is that if you take any row in the matrix, and this applies for all rows, the diagonal entry must be larger in magnitude, take the absolute value, than the sum of all diagonal coefficients for that row. Okay, also taken in magnitude. So shown here mathematically, the absolute value of AII, that's the diagonal entry, right? AII is greater than or equal than the sum of all off-diagonal components. If the system is not diagonally dominant, sometimes, most of the times, you can just rearrange it, move one equation and reorder the equations, and this is called pivoting. We'll talk about this in a second. That doesn't mean you cannot try an iterative method on a matrix that's not entirely diagonally dominant, but it will kill your iterative methods. There are actually methods that cannot work if the diagonal entry is 0, for example. Like the Jacobi method will not work. SOR, we'll talk about these. Pivoting. The idea behind pivoting is to turn a non-diagonally dominant matrix into a diagonally dominant one. There are two types of pivoting, starting with row pivoting. I'm just going to give you an example. You have these three equations where if you look at the first diagonal entry, it's 0. It's obviously less than 1 plus 3, which is 4. So that entry is not diagonally dominant. The other entries as well. So the last equation, there's 2 on the diagonal and there's 5 off diagonal. So 4 plus 1 is 5. So what we could do in this case, we could move the last equation, put it on top, and move the top equation and put it at the bottom. So what ends up happening, you get 3 on the diagonal for the last equation. We moved the first equation, made it last, and put the last equation on top. But don't forget to move the right-hand sides as well. Notice that the solution vector x1, x2, x3 does not change ordering. The only ordering that changed is row-wise. Now, a more interesting case is column pivoting, and I'm going to give you the same example over here. And we can exchange columns. So for example, if we swap the first and last columns, we can get a diagonally dominant matrix. However, you have to pay attention to the ordering of the solution vector as well, because as you move the 0, 0, 4 and 3, 1, 2, note that what they multiply actually. So the middle entry doesn't change because this is a symmetric and odd system that's symmetric really, but what you have to pay attention to is how you change the ordering of the unknowns. So in this case, to retain the original system, you have to make sure that you swap the meaning of what these unknowns mean. So if x1 and x3 stood for the temperature at point 1 and point 3, and then you swap them, you have to make sure that when you swap, you understand the meaning. When you look at the result, it's gonna come in the order x3, x2, x1 rather than x1, x2, x3. Okay, so we said that an iterative method essentially starts from a guess. Okay, it starts from a guess, and we start refining that guess. So the essential features of an iterative method are a guess, and then a recipe to improve the solution, and then finally a way to tell the recipe, the method, the for loop to stop the iterations. We will start by looking at the simplest, potentially least robust iterative method for linear systems, and that's called the Jacobi Iterative Solver. And going over the Jacobi method is really nice because it shows you kind of how the thinking about iterative methods starts and what we can do using numerical methods, the leaps that we can make using numerical methods. The idea behind the Jacobi solver is to be inspired from a single system, from a single equation. So for a single linear equation like ax equal b, typically this is very straightforward to solve, right? All you do is say x equal b over a, and bam, you have a solution, right? Okay, so what if now, let's take two equations and two unknowns, such as a11 x1 plus a12 x2 equal b1, a21 x1, a22 x2 equal b2. We've seen this standard nomenclature. And the leap we're going to make here is just the same way we did with a single equation. Let's take the first equation and solve for x1 in terms of everything else. So notice what we did here. We kept x1 on the left-hand side and moved everything to the right-hand side. So they gave us 1 over a11 into b1 minus a12 x2. Now, before you ask me what to do with x2, just bear with me for a second. And then for equation 2, we solve equation 2 for x2. Same thing, so you get x2 1 over a22, b2 minus a21 x1. Okay, this is great, but we haven't done anything, right? All we did was recast the system. It's still the same system of equations. Nothing has changed. We cannot solve it. We have to solve it. It's kind of coupled. We cannot solve for x1 without knowing x2 because x1 has x2 on the right-hand side. And we cannot solve for x2 without x1 because x1 is on the right-hand side. If we substitute x1 over here, you get essentially x2 equal x2. And so this doesn't help us. Okay, so obviously we need values for the x1, x2 on the right-hand side. And here is the leap that we make as applied engineers, as engineers, as numerical methods people, is that we say, okay, what if we start with a guess for those values? We pick arbitrary guesses, 0 and 0.5, 2 and 10, whatever, just 2 arbitrary values, okay, for x1 and x2. And to distinguish them from the x1 and x2 that are the true solutions, we're going to assign those a superscript, or a subscript if you want, as essentially a counter to say that these are guesses. And we're going to call these x1 0 and x2 0. So when you do this, you get x1 is 1 over a11 b1 minus a12 x2 0, where x2 0 is a guess where we started. It's a number that we know. So obviously, we can solve for x1 in this case because we know what x2 0 is. And same thing, we know what x1 0 is, so we can solve for x2. Okay, that's great. Now, when you think about this, you step back for a second and you're like, this looks like, these two equations look like actually a recipe that would update our initial guesses, x1 0 and x2 0, because they give us new values for x1 and x2. And then if we use those new values for x1 and x2 as guesses and then plug them back into this equation again, we can keep improving our guesses. Luckily, this works actually. And that's the basic idea behind the Jacobi method. So to make things clearer, let's rename the updates, in this case, this x1 based on x0 and x2 based on x1 0. Let's rename those to x11 and x21. So what we get, x11 is a function of this x2 0, which we know, and same thing, x21 is a function of x1 0, which we know. Now we know x21 and x11. Now repeat. We use those same values, x11 and x21, as our new guesses. And we use that same recipe to get another improved guess, x12 and x22. And notice how we use the x21 that we just computed and the x11 that we just computed. Now, same thing, x12 and x22 have been they're updated guesses, think of them. Now we use them to compute x13 and x23, and so on, all the way to an arbitrary number of iterations we call k. And in general, we get this formula, xk plus 1, x1k plus 1 is 1 over a11 b1, etc. And then x2k plus 1, that's the new iteration, is equal to something as a function of the previous iteration. Okay, this is really great. That's the essence of the Jacobi iterative solver. So show me an example. So take this system of equations. 4x1 plus 3x2 equal 10 and x1 plus 5x2 equal 14. We know that the solution in this case, if you run this exactly, is kind of 0.47 and 2.70 for x1 and x2. Let's say we want to use the Jacobi iterative solver, start with an initial guess, x1 and x2, initial guesses, x1, x2 equals 0. Then we do the first iteration, just like we learned, 1 over a11, b1 minus a12, x2, etc. So you plug in the numbers and you get these updated numbers, x11 and x21. Now you use those as your new guesses and run the same formula again and over again. And as you run this, after 100 iterations, you get pretty much very, very close to the exact solution. Now, obviously, we did this for 2 equations and 2 unknowns. We need to generalize this for an arbitrary number of equations and unknowns. Okay, so I'm gonna start by going to 3 equations and 3 unknowns, and then throw the generalization at you. Okay, So, for example, three linear equations. You have this system, A11 x1, A12 x2, and so on, B1, B2, B3, and we write this in matrix form. You get this 3 by 3 matrix. And again, we solve equation 1 for x1, we solve equation 2 for x2, and we solve equation 3 for x3. That's how you think about it, where I immediately use the counter. I didn't go through 0 in the initial guess and 1 and 2. I just used xk plus 1 and as a function of x8. So x1k plus 1 is a function of all the other x's at xk. Now, what I'm going to do here, I'm going to modify these equations because we know when we go and implement them, I want to simplify the implementation a little bit. What you notice in these equations is that on the right-hand side, what is missing is the diagonal entry. So there's no A11, for example, in equation 1, there's no A11 x1, and in equation 2, there's no A22, and in equation 3, there's no A33. And that's kind of part of the method. And when you go and implement this, this is really annoying to try to just sum the off, do the subtraction of the off diagonal elements. Okay, so what I'm going to do, I'm going to add and subtract x1k to the right-hand side of each of those equations. So what I did here, if you look at the right-hand side, I added x1k, so that's the kth iterate of x1, and I subtracted it from within the parentheses. And you notice there's an A11 x1k. You divide by A11, you get minus x1k plus x1k. It's exactly as it was before. I just manipulated this in a way because this implementation is easier. What I'm essentially doing here in the parentheses, I'm taking the right-hand side minus essentially the entire equation, okay, at xk. Okay, and so that simplifies the implementation, the programmatic implementation. Now, to generalize, it's kind of starting to look straightforward. You have x to the xk plus 1, the k plus 1th iterate is equal to the kth iterate plus 1 over the diagonal entry into the right-hand side minus the entire equation for the ith entry, okay? And you can generalize this way. This is the general form, xik plus 1. So this is saying that the solution of the ith entry, or at the ith row, or the ith solution entry, the new iteration is equal to the ith iteration k. So xik plus 1 is equal to xik plus 1 over the diagonal entry at that I. So let's think of I as the row, right? So aij is I is row, j is column, or that's kind of what we do in the matrix, right? So for the ith row, okay, we take the diagonal entry 1 over I into bi, the ith right-hand side entry, minus this sum aij xjk. That's nothing more than the entire equation. Okay, the entire ith equation, you just sum over j, right? So I is fixed. Now, another form that is simpler to program is when you're doing kind of vector, when you have vector-based code like Python, you can just do this in one shot, where you do the entire vector at k plus 1 is the entire vector at k plus the diagonal, 1 over the diagonal entries, so that's 1 over a11, 1 over a22, and so on, into b minus a xk. And that implementation only works really for the Jacobi. Once we go to more complex solvers, we're going to be stuck with the summation form up there. Now, another thing to notice with this summation over here, this is really nothing more than the dot product of the coefficients of the matrix on the ith entry. So aij, you fix I, you take all the j coefficients, so you take all of those coefficients on the ith row, okay, and you do the dot product with xk. That's the way to think about this, okay? aij xjk summation over j is nothing more than dot product of the vector in the matrix at the ith row dotted with the solution vector at k. Both of these you know. In Python, luckily, we can do this operation very easily. We can get any row we want in the array directly. Okay, and this gives us an algorithm. We start with a guess for xi. We update the guess for each xi. So we loop, we go over x0, x1, x2, and so on. And the formula for the update is given by either one of those. And then we repeat step 2 until the iteration count has been reached. And I went ahead and did the code, or I'm going to share this Jacobi code with you directly. You're going to have to modify it eventually in your homework. But what I'm doing here is, again, importing NumPy, etc. I'm not worried about this, but I'm defining a Jacobi function. Remember what we discussed in class. What do we want from a Python routine? A Python routine is going to take one or more inputs, going to produce one or more outputs. In this case, what I want to produce is the solution vector. Okay, just x. I want the solution. And what does the Jacobi method take? One could say it takes a coefficient matrix, a guess, initial guesses, a right-hand side vector, and a maximum number of iterations. Okay. Now, what I need to do first is get the number of rows and number of columns. So I call a.shape. That gives me how many rows and columns I have in the matrix. Obviously, you can do error checking here, make sure that n row, nr equal nc, so number of rows equals number of columns. And then I declare an iteration counter. I set it to 0. And then I declare a solution vector. I fill it with zeros. And so it's a NumPy array, the same size of one of the dimensions of the matrix, so number of rows or number of columns, they're equal either way. And then we start our iteration. We are just going to iterate until we hit the maximum number of iterations. This is user specified. And then we're going to loop over the rows, right? If you remember, the solution algorithm said we go over each entry I, okay? And we do new xi, so that's xik plus 1, and I'm looping here over I with a range from 0 to nr, which gives me 0 to nr minus 1 for a total of nr n rows entries, okay? So this is saying the ith row for I in range 0 to r, the ith row, that's xi, k plus 1 is equal x guess I, so that's k, xk, right? So that value is known, plus 1 over aii into bi, right? Everything is clear, minus, how are we going to do this summation? Sum aij xjk over j, that's simply the dot product of the ith row, the entries in the ith row of the matrix with the xguess vector, okay? And then we copy the solution, we put it in xguess, right? So, and we're doing this copy because we don't want to manipulate x, right? So we have to make a copy like we're used to in Python, and then we increment the iteration variable. We add with the iteration counter, we add 1. And once we're done, once this loops over the maximum number of iterations, it just returns x, okay? And here's an example showing how to use this. So let's kind of just run it in Python together. Let's create a new Python notebook. And the first thing I'm going to do is just put in the Jacobi Iterative Solver. Now, one little thing you have to pay attention to here is that this, okay, so just, we don't need the norm. Okay, this has to be a NumPy array in order to call shape, okay? Otherwise, we won't be able to do this operation, okay? So let's just deal with NumPy arrays from now on, okay? And now let's remember what our system of equations was. We had 5, 1, 1, 2, 3, 0, 3, 0, 4, okay, and 10, 11, 12. So let's go ahead and just declare the array. A is numpy.array. I'm gonna build it from a list of lists, okay? So we have 5, 1, 1, and then we had 2, 3, 0, and then we had 3, 0, 4 for A. We do print A, gives us this array. And For the right-hand side, we had 10, 11, and 12. Okay, and we can get the exact solution here. np.linalgebra.solve AB gives us the exact solution. Okay, now if you want to use the Jacobi method, okay, we're going to do simply x equal Jacobi. What do we want? What does Jacobi need? A coefficient matrix, x guess. So what do we want our x guesses? We can just guess is equal, let's say 0, 1, 0. Okay, and then guess, and then a right-hand side, and 10 iterations maximum. Then let's print x. So obviously it's starting to get close, but it's not quite close. If you change your guesses, you'll converge faster, but we're not going to want to worry about this much. We want to be able to converge regardless of the guess. But if we do more iterations, obviously we're going to probably converge, right? This is getting very close to the exact solution, which is 0.93, 3.05, and 2.30. Very close. Okay, now let's see how the iterations change. What I'm going to do here, I'm going to print the iteration and the solution. Okay, let's see. Okay, so what it's showing on the first column over here, there's the iteration, and this is x1, x2, x3, and this is how the values change as we go through. Obviously, as you can see, after some point, the numbers don't change much. And we're going to talk about this next time. The problem with using this approach right now, not the Jacobi itself, but using a fixed number of iterations, is that this can be inefficient, because how many iterations do you do until you know you cannot improve your solution? As we just saw, we stopped improving solutions at, let's say, at iteration number probably around 34. We couldn't improve much. So how do you choose that number? Okay, so we will talk about this in the next lecture. But for now, that's the first iterative solver that you will learn about.